Okay, some examples. Find the extreme values on f of x on the interval -3 to 3. Note, extreme values is asking for global extrema, and what they really want are y values. So just be aware of that. If I have f of x is that value, or that function, let's take the derivative. So I get 3x squared minus 12. And I want to set that equal to 0 in order to find critical points. So when I do that, I get 3x squared equals 12. Divide by 3, x squared equals 4. So I get x equals plus or minus 2 when I take the square root. Remember, plus or minus when you take a square root. Then I want to do f of 2 equals -21. I'm just subbing it in, and I'm subbing it in quickly so that this video doesn't take 25 years. I have f of 2 equals -21 and f of -2 equals 11. These are two values that could possibly be extreme values. Um, these are local maxes and mins. If I want to check whether they're local maxes or mins, I can make a little sign chart to kind of help my thinking. So I have -2 and 2, and then I sub in values into the derivative to figure out whether the derivative is positive or negative at these points. So if I sub in something that's like to the left of -2, let's say -10. If I sub in -10, f prime is positive over there. At -2, the derivative is 0. Let's say I sub in something between -2 and 2. For example, 0. If I sub in 0 to the derivative, I'm going to get a negative value. When I sub in something to the right of 2, let's say +10, +20, something like that, it becomes positive. So very clearly, based on what I know, at -2, I have a local max, and at +2, I have a local min. Those don't actually tell me whether I have the extreme values, but they at least tell me that I have a local max or min. If all I knew was this, I would think that f of -2 was my max and f of 2 was my min. But I also have to check the endpoints. It's very important to check the endpoints in any extreme value problem. You must check the endpoints. So in this case, since the interval is -3 to 3, f of -3 equals 4, and f of 3 equals -14. Once again, I'm just subbing them in really quickly. I'm using something, I already did it, but you would probably have to sub those values in, and this problem would likely be a no calculator problem, so you would have to do that on your own. So if I'm looking at this, the extreme values in this problem are the smallest value and the biggest value. So in this case, this is an extreme value. This is a extreme or a global min, and this one right here is the global max. The reason I know that is -21 is the smallest of the small, and 11 is the biggest of the big. And so those would be my global min and max values, and this would be what I would report. F of 2 equals -21 is the absolute minimum. F of -2 equals 11 is the absolute maximum. How would that change if my interval is -1 to 3? Well, I'm just going to kind of go through this on the other slides. So this was what I had originally. So my extreme values were, this was the original problem on -3 to 3. So I had f of -2 equals 11 was my max, and f of 2 equals -21 was my min. The local extrema were the same. Okay, and this is kind of what the graphs look like, all the points, and then here's the function zoomed in on -3 to 3. So as you can see, when it's zoomed in, this is definitely the highest value on the whole thing. This is definitely the lowest value, and they just so happen to also be local extrema. But if I take a look at the new window that I was kind of talking about from -1 to 3, that adds in another value. So at -1, we have 6. So that value is right here on the graph. And then when I zoom in here, this is kind of what the graph looks like. So my graph has has this -1, 6 going on as the highest value that I actually get. So I'm down to one local min or max on my window in my interval. So I only have one local min or max, and that's at f of 2 equals -21. That's a local min. And then I have to change what's happening with my global values because I changed my window. So f of 2 equals -21 is the global min, and f of -2 is no longer on my window. So now I have to redo this where I have f of -1 equals 6 is my global max, because that's actually the highest value. So this is just an indication that checking the endpoints is huge. You have to check the endpoints. You have to check the endpoints on these extreme value problems. Example 2, determine any points of inflection on f of x equals x cubed. I actually already kind of did this problem, so I'm going to go through this really fast. F prime of x equals 3x squared, f double prime of x equals 6x. So I actually kind of already did this a few slides ago when I was talking about stationary points. But if I'm looking at this, I want f double prime of x to equal 0, and that occurs at x equals 0. Now, when I take a look at these graphs, it's pretty clear that when I'm looking at f double prime over here, there is a spot where f double prime of x, if I'm looking at just a quick sign chart, it changes from negative to positive. When a function has the second derivative changing from negative to positive or positive to negative, then I have a point of inflection. So the point 0, 0 is a point of inflection. And if I'm looking at the original graph, it looks like it changes from concave down to concave up, which makes sense because it was negative, the second derivative, and it turns positive. So if I were writing this for the AP test and it was asking for a point of inflection, I would say something like at x equals 0, f of x has a point of inflection since f double prime changes from negative to positive. Example 3, the velocity of a particle moving on the x-axis is given by v of t equals t cubed minus 6t squared for the time interval 0 to 10, basically. When is the particle farthest to the left? That's asking a question of the absolute minimum of the position function. So we're actually looking for the absolute minimum of the position function, which would be something like s of t. But we don't have s of t, and we haven't learned integration yet, so we don't know how to find it. But we can use a little bit of thinking, and we know that v of t equals 0, or an endpoint are going to be the only things that we can think about. So let's set v of t equal to 0 and see if we can figure something out. So v of t, if I factor out a t squared, I have t squared times t minus 6. I want to set that equal to 0. That occurs at t equals 0 or t equals 6. Let's make a sign chart of v of t. I have 0, 6, and 10. The reason why I'm capping it at 0 and 10 is because I have boundaries for this function. So between 0 and 6, the velocity is negative when I sub values into my velocity. And it's probably easier to sub them in after it's factored. When I sub in values between 6 and 10, it's positive. So if I think about this using logic, I have a particle that exists only on the x-axis. It's going to start somewhere. The velocity is negative the entire time from 0 to 6. So that means it's moving to the left from the beginning until time equals 6. At time equals 6, it stops moving to the left somewhere and then starts moving to the right. And then it moves to the right until the end of the problem. So whenever t equals 6, it must be farthest to the left. So my answer is t equals 6. When is the velocity of the particle increasing the fastest? Oh, by the way, if I take a look at the velocity graph, that makes some sense. Because if I'm looking at this, my velocity is negative until here, and then it starts becoming, or I'm sorry, my velocity is negative until here. Um, this is actually the point when my velocity is most negative. And then this is the point when the velocity is 0 at 6. So v of 6 equals 0. When is the velocity of the particle increasing the fastest? That's talking about the derivative of velocity, which we call acceleration. So if we take the derivative of velocity here, we get 3t squared minus 12t equals 0. If I solve that, since I want it to be equal to 0 because I want to figure out local maximum values, I get 3t times t minus 4 equals 0. So t equals 0 and t equals 4 are my values where I can get this. So I'm going to make a little acceleration chart. I'm going to cap it at 0 and 10. Then I have 4. If I sub values in between 0 and 4, it's negative. Values between 4 and 10, it's positive. So when I look at this, it appears that 4 is actually a local minimum. So that means that that's not going to help me. So I have to check what my velocities increase or decrease is at the endpoints. So if I check the acceleration at 0, I end up with 0. And if I check the acceleration at 10, that's another endpoint. I'm going to end up with 30 times 6, which is 180, which is very large. So this is actually the time on 0 to 10 when the velocity is increasing the fastest. Okay, final point. What is the difference between a local extrema and a global extrema? For a function f of x, there is an extrema at x equals c if the following is occurring. Locally, both criteria must be met. Either the derivative is 0 or undefined, and f prime changes sign from positive to negative or negative to positive. That basically means f of x changes from increasing to decreasing or decreasing to increasing. So that's a picture that looks something like this. I have a local max here and a local min here. Globally, we only talk about it on continuous functions and closed intervals usually. There's exactly one global max and one global min, and it occurs either at an endpoint or one of the local maxes or one of the local mins, depending on whether you're talking about a maximum or a minimum. So that's the places where global max and global mins occur.